I'm Bill Robinson. This is Simon Watmough, and we're developers from Ape Games. So Ape is a game development company based in London, founded just a couple of years ago by some people from EA, Plainfish, Mind Candy, and a few others. And we've turned our years of experience across PC, Facebook, and console to developing free-to-play titles using Unity 3D. So Samurai Siege was our first Unity project and our first real success, coincidentally. It's a real-time strategy game with base building and combat and alliances, and we have lots of regular in-game community events and competitions.
So our latest title, Rival Kingdoms, is our attempt to try and improve on that. We've used the experience we gained from Samurai Siege to try and craft a richer, deeper experience in terms of like real-time strategy mechanics, the alliance mechanics, and also the look and feel of the game. So today we're going to talk to you about two of the most important things we learned through the development of these products, our content management tools and our approach to hacking. So let's start with content management. So even on mobile, most modern games have tons of content, and the guys that are touching that are usually not programmers. You've got designers, producers, all kinds of other roles. Also, as this is games as a service, you're going to want to change everything at any time without doing client and server deploys. You've got the Apple submission time to deal with, so you want to be able to move pretty quickly. So on Siege, our initial approach looked something like this. We chose Google Spreadsheets as our content management system. Now, that might seem a bit weird, but everyone knows how to use spreadsheets. So our designers, they work like this anyway. They can use the formulas to configure the HP between different levels, say, for example. And it's really easy for them to be able to bulk edit and create new content, create new levels. So that made a lot of sense to us. There's been a bunch of other nice benefits to that as well. It's cloud-based, so we can use it anywhere with an internet connection. It supports concurrent users straight off the bat, so you can share and collaborate on the same features in the same documents. And when you're a small startup, free is a pretty good price. So that's great. So next, we looked at the problem of communicating all this data between our clients and our servers. Initially, we chose JSON, but once you get to the kind of amount of data that we were going to be dealing with in production, it just wasn't fast enough. So we turned to a technology called Google Protocol Buffers. So here's the quote from the Google website. It's a bit of a mouthful, but the gist is it's like JSON, but faster, smaller, binary, and has really great backwards and forwards compatibility. So the first stage of working with protocol buffers is you build your message. So here we got a person with a name and an ID and an email. And then you compile that into language of your choice. So here's some Java code, which allows you to build and then serialize these objects across the wire. Cool. So as we said, protocol buffers were both faster and smaller than JSON. They're great backwards and forwards compatibility. And at the same proto definition files can generate your client and your server code, so you don't have any duplication bugs. It's not all roses, however. So the code that protocol buffers generate is pretty simplistic. So if you've got, say, a reference that points to a particular level of a troop via a string ID, it's your responsibility to join up all the dots between that data. It doesn't support dictionary types, at least not in the Proto 1 spec that we're using, but it does have in 2 and 3. That's a bit frustrating because it would have solved some of the problems with the lack of references. And then finally, it also doesn't have much support for inheritance. It's not the end of the world. You can just use composition, but sometimes it can just get a little bit unwieldy. So here's a more detailed version of the Samurai Siege CMS. We've got our spreadsheets being used by the servers. We've got our shared proto model, which generates the client and the server code, and our data being passed around as this efficient binary protobuf. But we still have these annoying handwritten layers of comprehension code. That's a bit of a faff. So that was all pretty sweet. We had this one great document that all the designers could collaborate on. It was really easy to access and to edit. And then we could communicate that around really quickly in really small amounts of data.
OK. So what kind of problems have we found with this system? So firstly, it takes quite a long time for the spreadsheet to load. Once we have a full game's worth of data in Google Spreadsheets, and the API is quite slow that you have to use. So when you're just trying to tweak one thing, a value just over and over to get it right, you can spend quite a lot of time just waiting for data to download. Also, if we want to add a new type or a new table in the spreadsheet, we need to add it to the proto file. We need to add it to the client code. We need to add it to the server code. Often it was just easier for us to just kind of jam some extra columns into an existing table, which is not that clean. And it's also a pain to maintain the consistency in these 3 places. So most of us end up having this spreadsheet open in a tab, almost all of us in the company, and mistakes happen, and it can be hard to track these down. Google does have a version history, but it's a bit slow. It's once you get to a big document, it's not really that usable. Also, it's quite hard to compare different versions. So we have lots of different versions for like our internal environments and our production, and then there's QA and loads of other environments as well. And kind of managing those, it gets a bit of a pain, and we end up with just loads of spreadsheets, which is ends up with quite a lot of maintenance to have to maintain all these different spreadsheets. So, I mean, this was on Samurai Siege. We were trying to get our first kind of success out. We were trying to make it pretty fast. We didn't have a lot of time to come back and like make everything really perfectly. With Rival Kingdoms, we had a chance to improve on some of these things. So one thing we really wanted to address is all this boilerplate code we have to write just to understand the proto model and make all the references properly. So we decided we want to rethink how we're generating code. Also, a lot of the problems that kind of come with all this copying different versions around and trying to merge things from spreadsheets to one another really gets solved if you just keep all your data in a version control system. So we kept it in Git. Our code is in Git. It was a natural choice for us. And also, a lot of the problems that are associated with the large spreadsheets we have to download and upload to the cloud all the time kind of go away once you're using a version control system. But we didn't want to lose the spreadsheets. They're too powerful to ditch. So we decided, let's just use local spreadsheets. Everyone can use their own spreadsheets, do whatever they need to do. So a lot of the kind of solution revolves around this piece of tech we ended up calling Super Schema. So it's a data description language, which we defined, which defines data structures for the client, the server, and the model. And it generates the comprehension code for us, as well as the existing protobuf chain being the same. And the great thing about this is it allows us to kind of, it's our own format. We can attach all our own metadata to it. So say we want to formalize the relationship between objects, like we have this building which has a projectile that it spawns. We want to make sure that it refers to something in the projectiles table, and we can, if we can annotate that, we can be sure we can write tools to test that and to, navigate those kind of things. Also, because it became easier for us to add new data types, we just have to add it to this thing and we get loads of code generated. It afforded better decomposition, more modularity. These things are generally good. So here's like a really simple diagram for what it kind of looks like. We have our super schema data we define. We have this compiler we wrote. And a lot of this code at the bottom is just generated for us. Once we kind of set it up, we didn't have to worry about it. So this is an example of what a super schema definition looks like. It's actually JSON. It maps pretty closely to protobuf, but we've got this crazy kind of type reference in here, which is a prefab. So I wonder what that could be. This is the same thing that it generates in proto. We don't have to worry about it too much, but here we can see the prefab has turned into just a string. And then we have this generated code. So we used to have to write this kind of stuff by hand. But you can see here, we've generated some code where you've got a prefab is just a property, and it goes and looks it up. And this is all generated for us, which is awesome. There's a bunch of server code also generated. We don't have to worry about that as client developers. But suffice to say, we edit the model. It gets updated. Our server guys are happy. Everybody's happy. So another problem we're having to solve, the way we addressed the data storage is we ended up sticking all our data into a version-controlled kind of repository, and we did that using JSON again, because why not? We love JSON. So, expanding on that diagram a little bit, we have our all the existing stack, and we are just storing directly from the protobuf model everything in a JSON data store, basically. I mean, that's it. So one of the key things we had to do, though, in order to make JSON really play well with Git, we had to make it merge with minimal merge conflicts. So the way we did it, each table became a separate directory, and within that, we had each row as its own file. So you immediately have kind of file level, row level isolation. And we pretty printed it, because as well as making it human readable, more lines, more separate lines works better with merging. Also, we added even more white space in between. So you see here there's commas in between even some of these fields. And this is just because if we have two fields changing independently, but are right next to each other, Git emits a merge conflict. But if you just separate them by something, kind of a static line of a comma, it actually resolves it. So that helped us a lot. Finally, we sort everything in alphabetical order where we can, just to keep it stable as much as we can. We didn't write our own JSON library. We took one off the shelf. It's on our GitHub page if you really want it. Also, we wanted to write an in-Unity editor. This wasn't strictly part of our plan, but we did it because we love using Unity, and we want to make sure we can use Unity the way it's meant to be done. So we have this super schema with kind of rich metadata about what all the data actually is and what things are, and we just kind of inserted this in here. It's still, we still use JSON as the data store. I mean, it all's just a view onto the data. This is what one of our editors looked like. I'm sure you recognize this style. This is our Canvas config example again, and here you can see it's turned into a nice Unity editor, and the GUIDs that were in there before are now just nice object fields, which is great. I mean, this is one of the real strengths as far as we see with Unity is like being able to make your own tools. This is another example. So we had, you can also annotate our metadata with like saying what specific things are, like, oh, this is a color, or in this case, this is some bounds around a specific part of an image. So we can make some really nice tools. It's really not that hard to make this kind of stuff in Unity. And still, spreadsheets. We want to keep the spreadsheets. They're just too powerful to lose. But again, this was just another view onto our JSON data store. And that was all great, basically.
So it turns out using local spreadsheets was a bit of a mistake. They're nowhere near as useful as Google spreadsheets. It wasn't the fact that we were using Google. It was that we were using it as our main storage for our CMS. Once we start using the JSON backend, the designers are just going to use Google Spreadsheets anyway because it's much easier and they can share it and they can collaborate. And they're just copy and pasting between the documents, it turns out. So we just gave them that power back and they can use it. Secondly, so since the introduction of IL2CPP recently, we found that a lot of our binary sizes have been bloated quite a lot by all the generated code being duplicated. So we spent a bit of time optimizing that. I know that a lot of the recent Unity builds have done a great job of reducing the amount of size that ILTCCP takes, but we wanted to get ahead of that curve and just really crunch down all that data. So some takeaways from the CMS side. The content metadata is super powerful. It lets you add all kinds of additional tooling around your stuff, and also lets you put in code generators, which are great for saving you a bunch of time running boilerplate code, and they prevent you making loads of simple duplication bugs between client and server implementations. And most of the useful tools we had were role-specific, so just like the Google Spreadsheets integration or the in-Unity editor for the developers, if you focus on a specific role, you get a much more benefit out of that. OK, so let's move on to looking at our hacking. So we had two main kinds of hacking. We had forged platform receipts. So this is where a hacker is sending you a receipt for, say, the Apple Store and trying to trick your servers into thinking that they've bought something that they haven't paid for. So these aren't actually that big a deal. As long as you're following the documentation from Apple and Google, you can detect those fairly simply on the server. But we do get a massive volume of them. Just people love trying their luck. So the second kind, however, memory hacking, is a much bigger problem. So here is an example of a memory hacking tool called Game Player. Basic premise is your hacker loads up your game inside their tool. They go search for the number of diamonds they have, say like 103, and it pops up right here. And then they can just go change it to whatever they want, so like 12 million, and now they never have to spend any money. So these do require jailbroken and rooted devices, but that's no big deal anymore. And they have to run it inside the app, but it doesn't matter. And they can only search for values that are kind of user-facing and they can see, or that they can guess that you might have behind the scenes. But they can change any of those at any time, basically. So on Siege, so simple validation. The way our servers and our clients interact, we batch up all the actions that you're taking over time, and then we send those to the server to kind of check what you're doing. So our servers are really geared around either validating that you've done something correctly or storing that for persisting it so that next time you start the game, you get the same world. Worth mentioning, our servers are written in Scala, and our client code is written in C#. So it's really infeasible for us to duplicate the entire battle engine inside server code. It would just be such a massive engineering task initially, and then the maintenance cost of all the gameplay changes we'd make after that would just be a nightmare. So walking through a simple battle hack example, say I start with my hacking tool, and I get into a battle, and I hack the health of a samurai up from 12 to 12 million. So now my one samurai just cleans up an entire base, and I win. And the server isn't capable of simulating the entire battle for the reasons mentioned. And so it just has to trust the client, essentially. So it'll put a loss onto the account of the victim, take some rewards away. And when the victim logs on next, he'll see that he was defeated. He lost some in-game currencies. But when he checks the replay, it'll all be out of sync, and the just normal samurai will be easily defeated. And players hate this kind of inconsistency. It undermines the whole of the game. So the initial approach we took on Samurai Siege was to essentially hash attack-prone data. So we would look at replays and identify which properties were being hacked by players, put in defenses for them, and then kind of release those builds out to the wild. But the entire thing would kind of rinse and repeat, and we'd get into a bit of an arms race, constantly having to be releasing. That goes against our games as a service kind of intentions. It's really just obscurity through obscurity. They don't know what we're hashing. They don't know how we're doing it. They don't know when we're communicating it backwards and forwards. And it does nothing to protect you against even more advanced forms of hacking, say like disassembling your code, rebuilding it with modifications.
Yeah, so we still do get some hackers slipping through the net, or with this system we did. So we already have players looking at replays when they have a hacked battle sent to them. Can't we just like fix the problem at that point? Well, we do record it, but we can't really fix it because it's, there's so much water under the bridge by that point that there's no really chance. The game state has all moved on, and because it's so interrelated, it's hard to unpick this. So it's just too high latency things that we can't rely on it. I mean, the other kind of solution, maybe we've got all these players playing, maybe we can get them to validate them in the background, but I think you'd say that's kind of ethically dubious at best, trying to get, like, would you do it in the back, you do it in the background? I'm on a mobile device, I have a battery, I might have even paid money for this game, I wouldn't want to go into that. So with the development of Rival Kingdoms, this was something else we had a chance to improve on. So really, the best way to detect these problems is to just fully validate the battle on the server. So we looked back at this again. We decided rewriting our entire server architecture in C# was just not feasible, as we said, and rewriting our battle engine in Scala is too expensive again. So, I mean, what else is there we can do? So we had a look at our kind of client architecture, and we try as much as possible to kind of separate our concerns like this. So we have our game engine, which is independent. We have everything that's in Unity is kind of just treated as a view. And we have our kind of commands, subsystem, and network, and the idea is that they're all nicely independent in theory. So the game engine, so this is we're more talking about the battle engine here. So we thought, how about we just wrap that up in its own little kind of microservice in a C# kind of mono runtime, and let's just use that for validating battles. So it didn't take that long to actually prove this concept could work. We just modified our build pipelines a bit of client code changes, and it was great. It looked like it was going to work, and we were just going to live happily ever after. Right, I thought I deleted this slide. It doesn't do that much. Receives battle in, runs a battle, sends battle back. That's it. So problems. There was naturally some nerves about this whole thing. We don't have much experience. We don't have any experience running mono servers ourselves. So we needed to prove out to our server guys primarily that this was going to be performant and it was going to be responsive. We have a live service. We needed to be responsive in all conditions, all loads. Also, a big problem running theme for us has been determinism, making sure that our game engine is properly deterministic, and simulating all our battles in this way really showed up some of the places where it wasn't. So we ended up making this kind of really terse logging format. We got to this as we were putting it out into our alpha and beta testers, and we started seeing battles coming back with no real obvious signs of hacking. It prints out the initial state and significant events. I'm not going to go into this too much, don't have much time. And then what we do, so the client would generate this. There's no point hacking it because it doesn't actually have any effect on the game. It's just a bit of debugging for us. And then the server that's validating these battles also generates it, and that gives us the ability to just look at it in a file differencing tool whenever we flag up that there's a problem, and we can really dig down and analyze what's gone on in this battle. And this has really helped us. I mean, it's so terse just because we're sending it along with all our requests, and we need to just crunch it as small as possible. Text was just simple. So what kind of deterministic problems were we running into? I mean, the most obvious, foremost one is probably how you manage your random number generators. So every game has pseudo-random number generators, pretty much. And you just need to make sure that you're using the right number generator in the right places, and that when you set up your battle, that the states all initialize properly and this kind of stuff. And also, there's some cases where you have users interacting with the game. They're dragging stuff. They're doing stuff all the time. Dragging troops, we found sometimes, because it spawns some virtual troops in, so you can see where you're going. And we have to make sure that kind of thing doesn't interact with our game engine, because that doesn't happen in the replay. We just see the troop appear. And then there's been lots of kind of platform-specific, small variations and edge cases. Floating point mathematics is a bit of a problem. So depending on the implementation, so we have iOS and we have Android, and we also have this battle validator on microservice. We need to make sure, we need to be really mindful of where we're using floats and exactly how we're using them. And also, with this kind of awesome IL2CPP tech that's allowed us to all get onto 64-bit with Apple, have come their own small sets of variations. But this is being iterated on rapidly, so I expect some of these things are just going to go away before too long. But the logging has been a really vital tool for us to weed out all these kind of problems.
So to recap, we got really great coverage from all different kinds of hacking from the validator tool. It led to improvements in the battle engine stability and also the replay stability. And we had a fairer game, so the community were much happier about that as well. So finally, the kind of too long, did not read version of this presentation. The content metadata is super powerful. It lets you do so many different things, including extra tooling like code generators, which is going to save you time and effort and fix you bugs. Most of the tools were specific, not generic. That's cool. It was important that we picked formats that were appropriate rather than just convenient. So way back at the start, if we'd just used JSON rather than sticking with the spreadsheet format we had, that would have been so much better for us in the long run. Don't trust the client ever. Don't believe it's lies. It's always wrong. Splitting your model and your view is something that most programmers know they should probably be doing, but there are so many benefits that you get from doing that in the long run, like the validator service. We couldn't have done it if we hadn't. And finally, some mad ideas are just really great, it turns out, like the battle validator. There was a slide for that, but it's disappeared, so never mind. Is it not working?
That's about it. No, I can't go forward.
We can't make the next slide come up, but never mind. If you have questions, we'll be in the speakers section, or if you look on our company website, you can find a way to contact us. Thanks for watching.